इस क्वेश्चन में हमें गिवन पीवी साइकिल को, ये जो कंप्लीट साइकिल है जो कि क्लॉकवाइज है, इस गिवन पीवी डायग्राम से हमें इन चारों क्वेश्चन को आंसर करना है। तो पहला क्वेश्चन है द वर्क डन बाय द गैस। जो ये कंप्लीट साइक्लिक प्रोसेस है, इसमें नेट वर्क डन कितनी हो रही है। सेकेंड पार्ट कहता है द हीट रिजेक्टेड बाय द गैस इन द path C to A and the heat absorbed by the gas in the path A to B, ये कैलकुलेट करनी है। थर्ड पार्ट है द नेट हीट absorbed by the gas in the path B to C and the fourth part is the maximum temperature attained by the gas during this whole cycle. So we'll start from part A. So the net work done by the gas is equals to the individual processes, because ये complete cycle 3 different steps से मिलके बना है, तो हम तीनों स्टेप का different work done निकालेंगे और उसे sum करेंगे to get the net work done. So work done during the path AB plus work done during the path BC plus work done during the path CA. So अगर आप path A to B देखेंगे तो it's an isochoric process and the work done during the isochoric process is 0. And work done from B to C. So clearly हमें मालूम है in a given PV diagram, work done from B to C can be calculated as the area under the B to C curve. So that is area under this shaded region that I am shading with the red pen. So clearly it's an trapezium, and since it's an expansion process, that is work done by the system in which the volume has increased, therefore it's considered as negative by the convention of chemistry. So half into area of trapezium is half into sum of the parallel side, that is 3 P naught plus P naught. That is sum of the parallel sides into distance between them, that is V naught. So this is the whole magnitude with sign of the work done in the process B to C. And the work done from C to A, as you can clearly see, it's a compression, that is work done on the system in which the volume has been decreased, and the work done from C to A is the area that I'm shading with this black pen. It's clearly in a square with length P naught and breadth V naught. So the work done in the path C to A is positive P naught V naught. So on further simplification, you will get net work done as minus P naught V naught. So that is the answer for the path A. Now coming to the part B of the question. The heat rejected by the gas in the path CA. If you see the path C to A, it's clearly a compression. So if you calculate QCA, and since it's a compression, QCA is delta U minus W. This is via first law of thermodynamics. So delta U is NCV delta T minus work done. And if you clearly see the temperature, the change in temperature here is the temperature at A is T1 and temperature at C is T2. So the difference is T1 minus T2, and according to question it's given 1 mole of a monoatomic gas. So N is 1, and for monoatomic gas CV is 3 by 2 R, and temperature is T1 minus T2, and work done from C to A that we have calculated here is P naught V naught minus P naught V naught. So 3 by 2 RT1 minus RT2 minus P naught V naught, and RT1 can be written as P1 V1 by 1, that is mole is 1, minus P2 V2 minus P naught V naught. And if you clearly see at temperature T1, pressure is P naught and volume is V naught. So we can write this as 3 by 2 P naught V naught minus, at 2 the pressure is P naught and volume is V naught. That is P naught twice of V naught minus P naught V naught. So on further simplification, you will get minus 3 by 2 P naught V naught minus P naught V naught, that is minus 5 by 2 P naught V naught. So the net heat rejected by the system, that is heat given by the system, that is considered as negative. So QCA is completely 5 by 2 P naught V naught. And the second part of the B question, the heat absorbed by the gas in the path AB. If you see the path A to B, it's clearly an isochoric path in which work done would be 0. If you see QAB, that would be equal to delta U, because work done is 0 because it's an isochoric process. And delta U is N CV, change in temperature. And as we move from A to B, temperature varies from T1 to T2. So N is 1, CV is 3 by 2 R for a monoatomic ideal gas, and delta T is T1 minus T2. And if you see at temperature T1, here the pressure is P naught, volume is V naught. So 3 by 2 RT1 minus RT2. So 3 by 2 RT1 can be written as P naught V naught by moles, that is 1, and RT2 can be written as, at temperature T2 the pressure is 3 P naught and volume is V naught. So RT2 can be written as 3 P naught V naught. So on further simplification, you will have minus 3 P naught V naught. So the heat absorbed by the gas in the path AB, that is QAB, is minus 3 P naught V naught. So this is the answer for the part B of the question. The heat rejected in the process C2A is minus 5 by 2 P naught V naught, and the heat rejected and the heat absorbed in the path A to B is minus 3 P naught V naught. Coming to the third part, the net heat absorbed by the gas in the path B to C. If we see the path B to C, it's clearly an isothermal in nature because the temperature at B is also T naught and the temperature C is also T naught. So in that case, in the C part, QBC would be equal to minus of work done, because delta U is 0 since it's an isothermal condition. And clearly when you move from B to C, the area under the curve will give you the work done, and we have already calculated the work done in path PC here, that is minus 2 P naught V naught. So if you put that here, minus minus becomes positive, QBC is 2 P naught V naught. Now moving to the last part of the question, that is the maximum temperature attained by the gas during the cycle. So firstly we need to find the relation between the given temperatures in this graph, that is T1 and T2. We need to find the relation between the temperature, and whoever is greater, either T1 or T2, will be the maximum temperature attained by the gas during the cycle. So if you see the path AB, it's an isochoric path because it is happening at the constant volume. So if you see in the path A to B, if you see in path A to B, if you clearly see, it's an isochoric process. So we can write in the option D, path AB is isochoric. Therefore, volume at A must be equal to volume at B, and volume at A can be written as nRTA by PA is equals to nRTB by PB. And if you see, the temperature at A is T1 and pressure is P naught, and temperature at B is T2 and pressure is 3 P naught. So putting that in this equation, we'll have N gets cancelled on both sides, R also gets cancelled. So TA is T1, PA is P naught, TB is T naught, PB is 3 P naught. So T2 is 3 times T1, and T1 can be written as P naught V naught by R. So the maximum temperature attained in the cycle is T equals T2, and that is indeed 3 P naught V naught by R. So this is the complete solution of this question and all four the parts.
Hello everyone. So we are given with the question which says 1 mole of diatomic ideal gas having a adiabatic index as 1.4 is taken through a cyclic process starting from point A. The process AB is adiabatic compression, BC is isobaric expansion, CD is an adiabatic expansion, and D2A is isochoric process. The volume ratios is been given VA by VB at 16, VC by VB as 2, and the temperature at A is 300 Kelvin. We need to calculate the temperature of the gas at point B and D, and also we need to find the efficiency of the cycle. So first let's try to calculate the temperature at B and D. So the given scenario something looks like this, and as we can have a look over here, A to B is adiabatic compression, B to C is isobaric, so pressure has to be constant. So B to C, C to D is again adiabatic expansion, and D to A is isochoric, means it is a isochoric process. Now we have to calculate temperature of at point B and temperature at point D. Alright, so since A to B is an adiabatic process, we can say for adiabatic the relation, the process equation is PV raised to gamma, and that is equals to constant, and we can write, instead of P we can write nRT by V. So instead of P we can write nRT upon V into V raised to gamma, and that is equals to constant. Since it's an ideal gas, so equation PV is equals to nRT holds true over here. Therefore from here we can say T into V raised to gamma minus 1 will be a constant. Alright, or we can say will be a new constant, but it's a constant value. Now as we have got the relation, so we can develop apply this equation. Let's say this is our equation 1 in the process A to B and C to D. Therefore we can get, so we can write from this, we can say TB upon TA, and that would be equals to VA upon VB. Since the relation is inverse over here, that's why we are writing we are following the inverse relation. All right, now from here we have been given with the ratio of VA by VB, and so we will substitute this value and we will get the value of TB. Therefore TA into this value, that is we can write TB, TB will be TA, that is 300 into VA by VB is 16 raised to 0.4. Alright, so this value comes out to be, 909 Kelvin. So we have calculated the temperature at B. Now we have to calculate the same process we will follow for the C to D process. We can write TD by TC, that can be written as VC by VD, the whole raised to gamma minus 1. But before that we have to check whether we have been given with Vc by Vd. No, so we have to first calculate the value of Vd, then we can apply this equation. So we proceed such a way that, so for this we have to first consider that we have been given with let's say Va by Vb as to be 16, and we have been given with the ratio of Vc by Vb as it's been given to be as 2. So therefore we can get the value of Va upon Vc, that is equals to 8. And if we carefully analyze the given diagram, so point D and A both will have the same volume, as the process is isochoric, so we can write Vd by Vc will also be 8. So this is just for the understanding we have written. Therefore we can write here it is the reasoning type. So we can say Td will be equals to Tc into Vc by Vd will be nothing but 1 over 8 and raised to 0.4, and that comes out to be the value of Tc is if we have a careful look, so the value of Tc, that is this value. Now to calculate Tc, first let's say we can have at pressure P, pressure at B and pressure at C is equal, as the process is isobaric from B to C. Therefore we can write this can be written as Vb by Tb, and that is equals to uh, Vc by Tc. Alright, therefore from here we can say the value of Tc can be written as Vc by Vb into Tb, Vc by Vb into Tb. Alright, and the temperature of Tb we have calculated as 909, so it can be written as 909 into Vc by Vb. The ratio has been given to be as 2. So this value comes out to be 1818 Kelvin. Alright, so this is also an reasoning for just we will use Tc as 1818 into 1 by 8 raised to 0.4, and this value comes out to be, therefore we can say the value of Td comes out to be, or we will just directly substitute it over here. So instead of Tc we will write it as 1818, and solving this value we will get the answer as 791. So 791 Kelvin. So the temperature at point D will be 791 Kelvin, and at TB it is 909 Kelvin. Alright, so this is the first part of the question. Let's now move on to the second part, in which we have to find the efficiency of the cycle. So we can write it as efficiency, that is eta, denoted by eta. So let's take over. Okay, so eta can be written as total work done or net work done upon heat supplied. Okay, so and into 100. So this is the formula for efficiency. So we have to calculate first heat supplied, that is QS. So as we can see in the diagram, A to B is an adiabatic process and C to D is again an adiabatic process. So heat will be supplied during this process, so the expansion will take place. So here it is heat supplied, and from here the heat has been rejected. Alright, so this is QR. So since heat supplied is during the isobaric process, so we will write it as heat supplied will be nothing but it is N CPDT. Alright, or this can be written as N, that is number of moles is being given to be as 1, so we can write it as Cp dt. Dt will be Tc minus of Tb. Alright, so here we can write Cp can be written as since we know the relation, that is Mayer's relation, Cp minus Cv is equals to R, and we know Cp by Cv is equals to the adiabatic index. From here we can say instead of Cp we can write, we can write R gamma upon gamma minus 1, that is adiabatic index minus 1, that into Tc minus of Tb. Alright, so solving this value, 1.4 divided by 0.4 into R, and Tc we have been given with Tc, we have calculated it as 1818, and Tb is 909. So 1818 minus 909, and that would comes out to be approximately 3182 R. Alright, so this is the value of heat supplied we have calculated. Now we have to calculate the work done. So net work done, that is we have to, now we can say W net is nothing but work done from A to B plus of work done from B to C plus of work done from C to D, and finally uh, work done from D to A. So we have to calculate all the four work done, and we have to just add them up, so we will get net work done. So from here we can write WAB, that is A to B is an isothermal, A to B is an adiabatic compression. So from here we can see the formula can be written as, for adiabatic process work done formula is it is we can write it as CV into TB minus of TA. So this is the work done formula in case of an adiabatic process. Alright, so CV can be written as we can write it as R by 1 minus gamma. In terms of adiabatic index we are writing this is TB minus TA. So we have to just substitute the value, and 1 minus that is, it comes out to be negative value, that is negative of we can say it as R by 0.4 into TB is been given to we have calculated it as 909 minus of TA is 300. So this value comes out to be this can be written as 2 by 5, so it becomes 5 by 2 R into 609 joules. So this is the work done from A to B. Calculate now work done from B to C, and that can be written as, since B to C is an isobaric process, so we can write it as work done can be written as P delta V in this case. Now this formula can be further modified as NR delta T. Alright, so this can be written as, since it's 1 mole, so R delta T, that is Tc minus of Tb, and Tc we have calculated it as, the value of Tc is 1818, and Td value is the value of Td is 791. So we can write here as R into Tc value is 1818 minus of value of TB is 909. Alright, so this value comes out to be 909 R. Alright, so let's check once again, the value of TB is 909. Okay, so let's proceed further. So this is the work done from B to C. Now we have to calculate work done from C to D. That is again an that is again an adiabatic expansion process. So we will be using the formula as CV into TD minus of TC. Again we can write instead of CV this can be written as R upon 1 minus of gamma, and it can be written as TD minus of TC. Alright, so this value is coming out to be negative 5 by 2 R into TD is being calculated as 791, and TC is 1818. So 791 minus of 18 and 18. So this value on solving gives us the answer as plus of pi by 2 R into 1027 joules. Alright, so this is the value of work done we are getting from C to D, 1027 joules. Alright, so now we have to finally calculate the work done from D to A. Therefore, we can write work done from D to A. Since it's an isochoric process, so work done will be 0, since we can write P delta V is the work done, and delta V is 0. That is, for isochoric process there is no change in volume, therefore work done is 0. Therefore now we can write uh, net work done can be written as we have got WAB as minus 5 by 2 R 609 minus of pi by 2 R into 609 plus of A2B B2C is 909 R 909 R, and plus of this is pi by 2 R into 1027. So solving this value we will get 909 R plus of, and this is 1, we can write it as 1045 into R, and while adding this to we will get the answer as 1954 R joules. So this is the total net work done we have calculated. We have kept the value of R as it is everywhere because we are trying to avoid the decimal part. So now we can easily calculate the efficiency, which is nothing but W net upon heat supplied, and that into 100. So we can write it as W net we have calculated the value as 1954 R divided by heat supplied can be we have calculated 3182 uh, 3182 R. All right. So from here we can divide both of this, and we will get the answer as efficiency in terms of percent. We will get it as, this is here, it is into 100. So this value comes out to be, solving this value comes out to 0.61 into 100, that is 61.4 percentage. So this is the efficiency of this complete cycle. So I hope you have understood the concept, and thank you for watching.
Hello everyone. So the question is, at 27 degrees centigrade, 2 moles of an ideal monoatomic gas occupy a volume V. The gas expands adiabatically to a volume 2V. Adiabatically, okay. Now calculate the final temperature of the gas, change in its internal energy, and the work done by the gas during this process. Now in the question they are saying that the process is adiabatically, and in adiabatic process the relation between the temperature and volume is given by the equation Tv gamma minus 1 equals to constant, and the initial volume is given in the question, which is V, and final volume is also given in the question, which is 2V, and the initial temperature is equals to the 27 degrees centigrade, or I can change it into Kelvin, so it is 300 Kelvin, and we have to find out the final temperature of the gas. Okay, so I am going to apply this equation for the initial and final situation. So it is T1 V1 gamma minus 1 equals to T2 V2 gamma minus 1. The value of T1 is 300. V gamma minus 1 equals to T2 2V gamma minus 1. So V gamma minus 1, V gamma minus 1 is cancel out. So the value of T2 is coming out to be 300 upon 2 gamma minus 1. And I can also write this as 2 1 minus gamma 300 Kelvin. So this is the final temperature of the gas. This is the first part. Okay, and in second part they are saying to calculate the change in internal energy. Okay, the internal energy is given by the formula delta U, which is my change in internal energy, is given by NCV delta T. Now gas is monatomic, and for monatomic gas the value of Cv is 3 by 2R. Putting the value delta U equals to 3 by 2 N R. N is number of mole, delta T is temperature difference. Okay, so it is final temperature minus initial temperature, and final temperature after calculating this value I will get my final temperature as 189 Kelvin. Okay, so the change in temperature can be written as 189 minus 300. 189 minus 300. Number of moles is also given in the question, which is 1 mole 3 by 2 into 1 into value of R is 8.314 into 189 minus 300. The value comes in negative, and which is equal to minus 21. Okay, after solving this, finally we will get the value delta U equals to, sorry, it's 111. Okay, when we calculate 189 minus 300, so it is coming out to be negative 111. Okay, the value is minus 111. Now solving this, we will finally get my internal energy, that is comes out to be minus 2767 joule. Okay, so this is my change in internal energy. And in the third part, they are saying to calculate the work done by the gas. Okay, so from thermodynamics first law, we know that the heat given to the gas is equal to the change in internal energy plus work done. Now the process is adiabatic, and for adiabatic process the heat is zero because there is no heat exchange between the system and surrounding. So in that case, my delta U equals to the minus W, or I can say W equals to minus delta U. And I already calculated the value of change in internal energy. So my work done is equals to the minus minus plus. So it is 2767 joule. This is my work done for this process. Okay. Thank you.